Assalamualaikum warahmatullahi wabarakatuh and very good day. My name is Muhammad Imran Helmi bin Othman, ID number 17007397, and today I will be presenting my final year project titled Modal Analysis of Double Cylinder Crank Rocker Engine. This presentation comprises of introduction, problem statement and objectives, scope of study, literature review, project flowchart, methodology, results and discussion, and finally, conclusions and recommendations. Firstly, introduction. The crank rocker engine is a novel engine design developed in UTP by a research team, and it was designed to achieve greater efficiency and compactness compared to ordinary crank slider engine currently in use. The development of the engine started in 2013, but there is still one problem to overcome, which is vibration. The single-cylinder crank rocker engine vibrates at random speed, and the vibration intensifies as the RPM increases, and resonance occurred. In order to solve the problem, the double-cylinder arrangement was proposed, and this project will be analyzing its vibration performance through the use of modal analysis technique. As you can see here in this top left picture is the real prototype of the 4-stroke single-cylinder crank rocker engine, while on the right side is the CAD model of its internal components and basic geometry. And for the bottom one is the double-cylinder crank rocker engine that has been modeled using Autodesk Fusion 360. Now we move on to the problem statement and objectives. This engine is a new design, and further analysis is needed to get the crucial data regarding the design. The vibration characteristics is unknown, and its natural frequency is also unknown. Therefore, without the information, we cannot determine whether the engine will experience resonance like the single-cylinder arrangement. Hence, the objectives of this final year project are to carry out modal analysis on the double-cylinder engine to determine its natural frequency and analyze the vibration characteristics of the engine simulated running at a range of speed. The scope of the study involves constructing the double-cylinder crank rocker arrangement using existing CAD models of the part, carry out modal analysis and vibration analysis on the model engine using MSc Adams, which is a multi-body dynamics analysis software, and then analyze the vibration characteristics and natural frequency of the engine. In order to gather knowledge on the subject of the research project, literature review was carried out continuously from the start until the end of the project. The literature review focused on 4 areas, which are the crank rocker engine, vibration analysis, natural frequency and resonance, and the modal analysis. As for the crank rocker engine is a novel engine design using a 4-bar mechanism and toroidal engine cylinder, as described by Kardan and Muhammad et al. The engine was designed to have improved efficiency and more compact compared to crank slider engine. Modal analysis on the single-cylinder engine by Rahman proved that the engine resonated both at low and high RPM, resulting in the violent vibration. Performance analysis was also done by Muhammad et al. That proved the single-cylinder crank rocker engine produced 6.28% more power and torque compared to a comparable crank slider engine. Vibration is a motion that is repeated in a certain period of time, as explained by Rao. Example of a vibration system are a pendulum swing and a guitar string. Vibration system can be simply expressed into 3 main components, which are the spring force, the spring constant or stiffness, and the spring deformation, which can either be extension or compression. As we can see here in this formula, the Fs is the spring force, the K is the spring constant or the stiffness of the spring, and the X is the deformation. Vibration can also be modeled in terms of conservation of energy, where the kinetic energy of the system is given as half times mass of the system times velocity squared, and the potential energy is given as half times the spring constant of the system times the spring deformation also squared. Natural frequency is the frequency at which a system vibrates without external force acting on it, according to Raynaud and Tucano et al. Every system has its own natural frequency, and when external force is applied onto the system, it will vibrate. As the frequency of the system increases due to the increasing frequency of the applied external force, the amplitude of the system's vibration will also increase. When the frequency of the vibration is equal to the system's natural frequency, resonance will occur. The vibration's amplitude will increase greatly when resonance occurs, and the system can be observed to vibrate violently. The formula below shows that natural frequency omega n is equal to the square root of the spring constant over its mass, and the frequency ratio R is given as the frequency of the vibration over the natural frequency of the system. When R is equal to 1, meaning the frequency of the vibration and the natural frequency is the same, the system will encounter resonance. Finally, modal analysis. Modal analysis is a method used to determine the characteristics of the system, which includes its natural frequencies and modal shapes, and formulating a mathematical model using the characteristics as explained by Jimin He. The method decomposes the system into its positions and frequency, allowing for linearization of the simple harmonics motion. The frequency of each mode shape represents the natural frequency of the system. Moving on, the project flowchart explains the flow of the project from its start to its end. In the beginning, we have the reviewing of past literature on the engine design and testing methodologies. After that, the 3D CAD model was acquired, and the model can be assembled and loaded into the simulation software, which is MSc Adams, where in the software we can define the parameters such as the bodies, the joints, and also the measurement points. After that, the engine was simulated running at different speed, and also the model analysis was carried out. The data was collected automatically by the software, and then the data can be interpreted. If the data is not as expected, we go back to the assembly of the model and loading into the software. After that, the discussion and conclusion as well as the recommendation can be made, and that is the end for this project. Now we move on to the testing methodology. The first step is to assemble the engine from the parts CAD models using Autodesk Fusion 360. After that, the assembly is imported into MSc Adams, and the model was prepared by defining the joints, bodies, and reference points for data collection. As you can see here in the second picture, the red element there are the springs elements that are used for the data collection. The third step is to run the normal mode vibration analysis using MSc Adams Vibrations plugin. And then after that, the engine can be simulated running from 500 RPM to 3000 RPM in 500 RPM intervals. Data from all simulation runs will automatically collected by the software, and it can be viewed and exported using MSc Adams post-processor. Excel was used to analyze the data and to plot the graph. Up until this point, if there was any ambiguous results, the steps were repeated from the start to trace any mistakes or errors. Finally, from the data, conclusions were drawn and improvements were suggested. As with the project flowchart, the Gantt chart shows the flow of the project, but also the timeline and milestones of the project. There are 6 milestones throughout the project, and by using the Gantt chart, the progress of the project can be monitored from time to time. On the left side here is the FYP1 Gantt chart, and the milestones for that is the proposal defense, submission of the interim report, and the submission of the full interim report. For FYP2, which is this current semester, we have the major milestones being the submission of the draft dissertation, the Viva virtual presentation, and the submission of the project dissertation in hardbound format. Here we have the 2 result cells for this project, which are the undamped natural frequency and the vibration response frequency. The undamped natural frequency is the result for the normal mode vibration analysis, while the frequency response is the results for the vibration analysis of the engine running at different speed. As the table shown, the engine has a natural frequency between 1.94 to 2.23 Hz for mode shape 1 to 6. This is very low for this engine, and since it does not affect in terms of the resonance, they are not the focus for this project. For mode shape 7, 8 and 9, the natural frequencies are 86.63, 167.53 and 187.29 Hz respectively. This is the three frequencies that will be the focus for this project. As for the vibration response, when the engine was simulated to be running at 500 RPM to 3000 RPM, the vibration frequency are between 8.75 to 50.35 Hz. From these two tables, none of the frequency values coincides, and such it can be concluded that the double-cylinder engine will not encounter resonance. Further analyzing the data, the frequency response against the speed of the engine was plotted in Excel. The graph has a linear shape, and using the built-in projection tool, the frequency response of the engine was projected until reaching the speed of 10,000 RPM. It can be seen here in the graph that the engine will only resonate on the 7th mode shape when the resonance frequency is 86.68 Hz, and the speed of the engine at that time is around 5,000 RPM. And the engine can safely operate up to 10,000 RPM without encountering the second mode shape, which is at around 187 Hz. In conclusion, the vibration of the engine when operating at 500 RPM to 3000 RPM does not coincide with any of the undamped natural frequency of the engine. Resonance will only occur at around 5000 RPM based on the forecasted data, and the engine can operate until 10,000 RPM without resonance occurring again. The double-cylinder crank rocket engine managed to solve the vibration problem faced by the single-cylinder engine, and in the future the engine prototype can be manufactured and further testing such as using biofuel as the fuel source can be carried out. For future works, the components for the double-cylinder engine such as the crankshaft, the engine block, and the engine casings must be designed since it will increase the accuracy of the results instead of using the single-cylinder parts. Using multiple engineering software such as Altair, OptiStruct, and ANSYS to carry out the model analysis will also cross-validate the results and improve accuracy furthermore. That is all from me today. Thank you.